Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at a unique case for the two behavior characteristic of the partition function for diatomic molecules. And this, of course, is the concept of a summation that we had given, which basically concerns the aspect of a quantized behavior, and of course the characteristic behavior for classical behavior, which basically I had mentioned as integration. Now, in this case, I'm going to use the general representation for the rotational partition function of a diatomic gas, and of course, those are going to assist us find an expression, of course, which is going to be giving us the general or the final result for the partition function of a diatomic gas. Now, in this case, given the general representation for diatomic gas by considering the aspect of degeneracy and the Schrodinger's equation. And we had come up with a general representation for the rotation partition function of a diatomic gas given as the summation from J is equivalent to, so this is a quantum rotational number, and then this is going to be from J to is equivalent to 0 to infinity. And we had said that this is basically given in terms of 2J plus 1, which is a value of G, Ti, and then we had this one as an exponent of this specific expression. Now we had considered this rotational constant of B and given it in terms of, so we had decided that basically this rotational constant represents the square of Planck's constant, and of course given as a ratio with 8 pi squared over the moment of inertia, and therefore we had done a substitution for that one, and this one gave us y h squared all over 8 pi squared I kBt, and this of course gave us a general formula for giving the rotational function in consideration of this specific aspect of energy as per of course Erwin Schrödinger. Now in this case I'm also going to expand this one, and we have decided that we are going to consider the aspect of a rotational temperature, which we have given in terms of this theta r, and theta r we said is going to be given in terms of 8 pi squared I and then kb, and that of course represented our aspect of the rotational temperature, which we had given in terms of theta. So basically for this one I can just give it in terms of theta r, and we said that we can substitute theta r in our specific expression above and come up with another version of representing this partition function, rotational partition function, using this specific rotational temperature, and therefore this gave us an equation of the summation over J0 and then 2J plus I for G, and then we had the exponent of negative J into J plus 1, and then we had this one over T, and then we had this rotational temperature. So this basically was a simplified version of that specific partition function considering this kind of rotational temperature. And of course I had mentioned that we are going to, this expression is going to be quite relevant for us in determining whether a molecule is going to display the classical quantum behavior depending on various temperatures. Now there are given two conditions whereby if you consider the energy which is going to be obtained to be much smaller than the value of kBt, that one implied a classical behavior, and if the energy which is going to be obtained is much greater than or the value of kBt, then that one implied a quantum behavior. And in this case, the energy that I'm mentioning in this case has got these two specific conditions, which I've said if this is much greater than the value of kBt, then this one of course implies a quantized behavior, and the reverse of this is going to imply of course a classical behavior in that specific respect. Now in these two states we're going to consider the concept of also the temperature with respect to the, or the normal temperature in Kelvin scale with respect to the, of course, rotational temperature, whereby in the first case, if the energy is going to be given in this specific case, which is much greater, then that one will give an implication that the T is much of course, smaller than the rotational temperature, and that's, as I said, is going to give us a quantized behavior. Now for these two states, for the quantized and the classical behavior, we're going to find a way of perhaps trying to do a replacement for this summation sign by introducing an integrational substitution and see what is going to happen. So we can just do a reduction of this specific formula by considering the various aspects, whereby we are going to let a value, an arbitrary value, represent one of the aspects, whereby if I say x is going to give j plus 1, and of course if I give another value which is basically a form of a derivative, dx is going to represent, or of course an integration is going to represent 2j plus 1, which is a degeneracy, and therefore this is going to be given in terms of a dj. So we're going to consider these two states and do a substitution in this specific formula, and therefore this is going to give us a partition function, a rotational partition function given in terms of the integral now between 0 and infinity. So this is a substitution of this, and then we're going to have this one given in terms. So if you do a direct substitution for this specific element for, of course, x and dx, so we're going to do a replacement for these two specific elements in the values of of course the specific elements which are going to appear having these specific components. So for 2j plus 1, we're going to do a substitution at this specific point, and for the j into j plus 1, we're going to do a substitution at this specific point. So this equation is going to translate into an expression of this specific form. On the right side, I'm going to have this one over t, and then we're going to have x into dx given as such. So basically it's going to be the exponent over this specific value, the exponent of j, the exponent of this specific value, which is the rotational temperature still is within this exponent value, and then we're going to have the value of x, which is this specific value at the top, the numerator, and then t is going to be maintained as that, and the value of dx basically is going to appear at this far end, but our dx is representing this specific 2j plus 1 given at that specific point, and of course that's going to be representing our replacement for that specific value of dx, which is going to give us this particular component. Now remember, the concept of a dj that is going to appear at this specific point is due to the concept of integration, which we had considered in this specific case. So therefore it's going to be appearing in that specific format, and therefore we are going to have this rotational partition function given in terms of so we're going to consider substituting for those two values of 0 and infinity for j, and this is going to be a rotational temperature and the exponent of rotational temperature over t, and the exponent of negative rotational temperature over t, and then this is going to be between 0 and infinity. Remember, the second aspect of this, treating this specific exponent, is from the laws of logarithms, whereby we say that if we have an exponent of this nature, then we're going to take that specific value for the exponent, and it's going to form some kind of a coefficient, a numerical coefficient of algebraic representation, and therefore this second aspect of this particular equation for the representation, which has been given in brackets, I presume it's going to be comprehensible for us, and we're going to have this second aspect given in that specific order. Therefore, by doing these various substitutions, we're going to solve this one equation between 0 and infinity for the values that we have mentioned for basically this specific range for j, and of course this is going to lead to a specific representation, which is going to give us a final result for the value of the quantum, the rotational quantum number for the diatomic gas, which is going to be given in terms of QR is equivalent to T 1 over the rotational temperature given as such, and of course this is going to be still equivalent to a value. So we're going to do a substitution for that rotational temperature, which is of course 1 over, so it's going to be 8 pi squared the moment of inertia kBt, and of course 1 over Planck's constant given as the square of that. So in this case we have included the temperature as the rotational temperature, we have included a T. And this is going to be the final representation for the rotational quantum number of an ideal gas of a diatomic molecule given in that specific representation. So I hope that we're going to follow up these steps one by one, and of course find various ways of representing various aspects of matter, especially for the gases, liquids in that specific case, for which we said for going to display continuous and or distinguishable and distinguishable kind of particles. And of course, they are going to assist us in evaluating various problem sets that we may come across in our various discussion. So that is it for now, guys. Bye. God bless you. Catch us in our next video.